So we looked at the idea that the basis vectors in a two-dimensional space, x and y, right? So I hat and j hat, right? The x and y directions in a flat space, those are always fixed. And so if we have a vector field with components, an x component and a y component, then we know that if we take derivatives of this vector field with respect to some coordinate, let's say x, we end up getting the derivative of the x component, I hat, and then let's just write it out fully. Then we have ax derivative of I hat with respect to x plus ay derivative of that with respect to x and this, because I hat and j hat are not functions of x and y, this simply becomes that. But if we have different coordinates, then this is not the case, and then this is going to be the object that once we get this object, so we want a more general expression that involves the derivatives of the vectors that give us information about direction, the basis vectors. Then we can generalize this to curved spaces. So let's say we have a vector A, maybe we can be specific, let's say in r theta coordinates, so the radial component, and there's a unit vector r hat plus there's a theta component and a unit vector theta hat, and the derivative of A, let's say with respect to the r coordinate, looks like derivative of AR with respect to the r coordinate times r hat plus AR dr hat with respect to r plus dA theta with respect to r theta hat plus a theta d theta hat with respect to theta. Or we could write this as, let's write it here, dA with respect to r equals d by dr of, let's use the summation convention. So we have the component and we have the basis vectors, call them E beta, and you put an arrow like that on them, and this gives us dA beta vector r E beta plus A beta. So we have to sum on these, derivative of the basis vectors with respect to r, and we can generalize. So let's generalize from r to some coordinate x with a different index, so alpha, and this becomes derivative of A with respect to x alpha equals derivative of what we have here, A beta with respect to x alpha times the unit vector with respect to x alpha. And this object here is usually written, so this is a vector. And so here we have components with the basis vectors. And so d e beta, right, how is this vector changing with respect to this x alpha coordinate? That is usually written in terms of this connection coefficient, which we'll explore in more detail. So if we look at gamma, mu, beta, alpha, this is the muth component of this object. And so this object depends on the coordinates we're using and on the space. In particular, it will depend on the quantities that go into the metric tensor to determine distances. So let's write this. Using these quantities, we can write dA with respect to x alpha as dA beta with respect to x alpha e beta basis vector plus a beta. Now using this, we'll write components beta, alpha, mu, e, mu. And then, because the basis vectors are, we're just summing on these beta and mu and here beta, we can write this as, so that we can see the common basis vectors, write this as dA beta x alpha, e beta, leave this as it is, plus a mu gamma beta mu alpha e beta, so that these are the same, and therefore this becomes the component. We can separate out the component of this new vector. And throw in the basis vectors like this. So this is a general expression for the derivative with respect to x alpha of a vector field in a situation where you have the basis vectors are changing in space, and this is going to be the object that we need in curved space. And eventually we'll move to curved space-time, and we'll have the same machinery, and we'll be able to derive, for example, the important equation that tells us how objects move in space when there is no force acting on them. They're just moving through curved space-time.